Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. All right, everyone. I am here at NeurIPS continuing my coverage and conversations from the 33rd NeurIPS conference, and I am seated with Pablo Samuel Castro, who is a staff research software developer at Google. Pablo, welcome to the TWIML AI podcast.
Thank you. Thank you very much for having me. This is a real pleasure to be here. I'm a big fan.
Awesome. Thanks so much. I am really excited to jump into this conversation. You are someone that I follow on Twitter, and we've had these kind of occasional back and forths over time, and it's great to finally meet you in person. You've got some pretty varied interests. You spend a lot of time, your research focus on reinforcement learning. You also tweet a lot about music and the arts. Looking at your background, you've done applied ML stuff at Google on, ads, Chrome, and other things. Tell us the story. How do all these threads come together?
Originally I'm from Ecuador, and I moved to Canada after high school to come study at McGill. So I did my undergrad, and then I eventually actually did my master's and PhD at McGill with Doina Prikup and Prakash Panagadan. And so part of the reason why I stayed in Montreal and McGill was for personal reasons. I was dating someone who's now my wife, and I also
personal reason?
Yes, and I also had a band. So I've always been heavily involved with music. I grew up with music, learning music, playing music. So that was very important to me, and I didn't want to leave that. So I decided to make that choice. I know it's not the typical thing that is suggested to do all your degrees in the same university, but for me it was more important to keep playing music. So I finished my PhD at around 2011, and then I moved to Paris for a postdoc. And this was at a time where AI isn't what we see here with 12,000 people in this conference. I mean, NeurIPS didn't have, back then it was called NIPS, maybe 4,000 people. So I wanted to stay in academia, and I was working at this intersection that was very theoretical, sort of between Markov decision processes and formal verification. So I was finding it really hard to find a job because I wasn't formal verification enough for the formal verification community, and I wasn't reinforcement learning enough for the reinforcement learning community.
Okay.
And so after my postdoc, I just feared, I already had 2 young kids, and I feared that I would just be going postdoc to postdoc for too long. So I luckily got a job offer from Google doing applied machine learning and ads, and I actually said goodbye to academia at that point. I stopped reading papers, and then I did a little quick stint in Chrome doing building machine learning infrastructure, so back-end infrastructure. And Brain opened up in Montreal, and Mark Belmar, who I had done my master's with, he kept in research. He was in DeepMind for a while, and he was one of the first people to join Brain in Montreal. And he put in a good word for me, and so then they offered me to join them, and I jumped at that possibility. And I hadn't been following the research at all, so it was a huge shock to come back. I mean, when I was doing my research, we were all working on grid worlds and very simple environments, because a lot of it was theoretical. We didn't really use deep networks at all for reinforcement learning. So it was a lot of catch-up, trying to familiarize myself with the literature and how the whole landscape had changed. So throughout all this time, I always kept with music. I had a few different bands. I've always been performing live and writing music. And the other thing is, when I started my PhD, I was actually considering doing a PhD with Douglas Eck as well as with Doina Prikup in something with machine learning and music. But at the time, what was available for music generation didn't really excite me very much, because it was still in the early days, and I feared that it would taint my love of music, and I just wanted to keep my music side separate. But when I rejoined the research world and I saw what the Magenta team was doing, I was kind of blown away by the quality of things. So then I decided to also start going along that pathway. And I think the day after I joined Brain, this artist from Canada, he's called David Usher. He's pretty well known in Canada. Okay. He approached us wanting to... The other Usher. He approached us. He was actually first. He had a band in the 90s called Moist, and it was really popular. And he approached us. He wanted to do an album using AI techniques. Okay. And so we just met and kind of brainstormed. And the thing he gravitated towards the most was lyrics. And so Hugo La Rochelle, who was my manager at the time, was very generous because I had just joined Brain. He's like, "Do you want to take this project?" Because I like music. I said, "Sure, it sounds fun." I had never trained a language model. I was still trying to figure out all this deep network stuff because I hadn't looked at that. But yeah, Hugo gave me that opportunity, and I learned a ton in that project. And so it's still an ongoing project. So relative to the first model that I trained with David, which we actually made a video out of that. Like he rewrote one of his songs with this first prototype, and it worked okay. But the model we have now is so much better, and I understand all of this language modeling so much better than when I did before. And that's just, that experience kind of showed me to not be afraid of sort of stepping out of, because I'm very familiar in reinforcement learning, which is my background, to step out of that comfort zone and go into other areas that I'm not as familiar with, because they're all interesting problems, and sort of really trying to dig into the details. For me, the way I learn the most is actually trying to implement some of these models and architectures and play around with them, because you read about them in papers and you kind of get it. That's fine, but until you're actually trying to get it to work for yourself, that's a whole different experience. And I've learned so much just from doing this, like jumping from one problem to the next in a separate kind of field, and learning about those architectures, but while still maintaining my research and reinforcement learning.
Well, it sounds like you've landed in an incredible place to do that, not just kind of the resources of Google and the people that you're surrounded with and have an opportunity to interact with, but your role seems to be defined as like advancing research, via implementation.
Absolutely, yeah. So I'm a software developer, like that's my official title. There's also research scientists at Google, and until recently there were still, like, most people that are in research want to be research scientists, because that's like then you're officially doing science.
Right.
So if I had graduated, say 4 years after when I graduated, likely I would have been applying for a research scientist role. Back when I applied at Google, that wasn't really, maybe Sami Benjo was a research scientist, but probably that was about it. And so I entered Google as a software engineer and sort of advanced my career in that track. And when I joined Google, it was as a software engineer, or we call it developer in Quebec, because engineer, you get an iron ring, and I don't have that iron ring. Initially, I was a little skeptical because the official description is you're there more supporting research scientists. And so I was worried that I wouldn't have the flexibility to sort of pursue my own research interests, but it's been not at all like that. So I lead my own research projects, and I still support a lot of people with the engineering aspects of it, because I've been working on this a lot, so I'm more familiar with like Google infrastructure and just coding in general. And it's been, a lot of the major advances that we see in machine learning and AI nowadays a lot of it is engineering. So there's still math and there's still a lot of theory behind it, but a lot of it is engineering. And I don't think I think more and more it is, but a few years ago, I don't feel it got the credit it really deserved. And so living in this sort of intersection of pure engineering and pure research is, for me, super exciting, because I kind of get to play around in both worlds and learn from both worlds.
I've got a long list of things that I want to talk to you about, but you mentioned something that's got me really curious. What it means to evolve a language model. You started this project with David and came out with this, early crappy language model, and have evolved it over some number of years.
It's been it's been like a year and a half. It's been almost like 2 years, I think, since we started it. But 2 years calendar wise, but it's not one of my main projects. So yeah, exactly. Sure. So it's when I get a chance that I work on that. So as I said, when I started this project, I had never trained a language model. I knew what LSTMs were because I'd studied it in school. But so the first thing I did was I actually, Andrei Karpathy has this famous blog post, the surprising reliability of recurrent neural networks, something like that. Anyway, so I read that blog post and I got his code and sort of played around with it, and that was the V0 model, just over characters. And then I started tweaking that a bit and finding new data sets for lyrics, and that initial model, that was basically a variant of Andrei Karpathy's model, was the initial model that I had. And so that was like just a milestone, I was able to train this and actually get it to do what I wanted it to do. But it obviously it has all the shortcomings that these types of models do. at this around, I mean, the attention is all you need paper had come out not too much before then. And so then I started looking into these attention models, and so it seemed like the right thing to do. So I switched over to the transformer model and started playing around with that. And so the V2 model was using an attention model. And so I had various versions of V2. Part of the difficulty that I had with the language, with training these language models on lyrics dataset is that the lyrics dataset is not the best.
In what sense?
So the tricky thing about these language models is that, and for lyrics in particular, is that you're trying to get this model to learn English, kind of. So how to structure English phrases together, but in a quote unquote poetic way,
right?
And to not be boring, right? Because you're trying to use it for creative purposes, and so you don't want it to be boring. So we trained this model, and if you look at like perplexity scores and things like that, it was doing pretty well on this lyrics data set. But then when you actually look at the output, it was extremely boring. So because in pop songs, you have lines that repeat often. I mean, that's just how songs are written. So the model would tend to just repeat the same thing over and over and over again. It also had certain phrases that it would keep on coming back to, like they just had very high likelihood. So when everyone talks about this, I say like it's hand wavy, but the average pop line over the last 6 decades is, you know that I'm the one. And so that one came up a lot. And you can also add, sometimes you get, you know that I'm the one, comma, baby. So that's the average pop line. And it was boring. And so the interesting thing about working with David is that I'd build like variants of these models and I'd show him. And one of the things he remarked on is that it was very non-specific in the sense that the nouns that it was using, it wouldn't use proper nouns. So it would use like me, you, he, she, they. So it's very kind of ambiguous if you think of like the Beatles. I mean, there's Me, Mr. Mustard, Polythene Pam, Jude, you know, there's all these, I mean, they're fictional characters, but they're characters, yeah. And so then you can sort of, they ground the song in something kind of real. Whereas if you're just talking about him, like, hey, you, don't let me down. Like that's not, even though Pink Floyd has a Hey You song. So anyway, then from that feedback, I started looking at other data sets. So for instance, the fiction books data set. These are available online. So we trained it with that and we got much more diverse vocabulary, much more diverse themes than we would get with lyrics. But the structure of what was coming out no longer looked like a song line, like a song lyric. It looked more just like a sentence that you sort of cut in half, and it just looked like a sentence with new line characters thrown in random places. So then I thought, why not, rather than trying to tackle this problem with a single language model, where I'm trying to get all these constraints of like being coherent from the English perspective, being kind of creative, and also following the structure of lyrics, why try to do this all with one model? Like for me, there's no.
Before you go to multiple models, with the language models you were working with at the time, is there a way? Are you trying to express those constraints explicitly, or just based on the data that you're feeding into them?
I was more playing with the data. So with the training data that I was using to try to enforce these constraints. So the lyrics, I mean, the idea was, well, if we want to write lyrics, then we should train on a lyrics data set to try to replicate that distribution. Right. But there's, as I'm saying, a lot of the interesting lyrics are in the long tail of the distribution, and the long tail is terrible for a model because it's going to have low likelihood by definition. But that's actually what we're interested in. So it has to be coherent but unlikely. And so that's part of the reason why I was considering just going to why try to do it with a single model. As my ultimate goal was to have something that artists could actually use, and David could use for writing a whole new song from scratch. And so for him, it doesn't, like, he won't care, and most artists won't care whether it's a single model or multiple models, as long as it is interesting and makes sense.
And just to understand the goal, is it start with some prompt and the thing spits out an entire song, or kind of is the model one in which the artist is kind of incrementally prompting the model and kind of refining the output?
Yeah, it's more the latter. So the way we're starting to build out a website that I'm hoping to release early next year. So it's almost ready, but it's just, as I said, it's one project that I work on when I have time, and with NeurIPS and all that, it's been kind of tight. But the idea is, you have kind of like almost like a notepad where you're writing your song, and this is coming a lot from feedback from David about how he writes songs, and so you write your part of your line, or you can even start without a prompt and then just ask the model for suggestions, and so then the model will give you suggestions for the next line. You can specify rhyming schemes, so whether like if you want ABBA or if you just want it to rhyme with your current line, and then the model will give you some suggestions, and then you can like drag those suggestions over to your worksheet, or inspire yourself from the suggestions that the model gave, and then continue working with your song this way. So it's more what I'm not as interested in is having something where you press a button and it produces your next top 40 hit. It's really like a tool, the way I view it is as a tool. So one analogy I like to use is, if you think of recording music in the 60s or 70s, if you wanted to record a good album, you had to go to a professional recording studio and hire a professional recording engineer, because otherwise it wouldn't sound very good. Now we have things like Pro Tools and Ableton that you can do it in your basement, and like a lot of people have become very famous from recording albums completely by themselves in their basement. So it's not like we got rid of recording engineers or recording studios. They're still around and doing the same thing, and you still require them for many purposes. But these tools like Pro Tools and Ableton kind of democratize the recording industry, and so a lot of people can start playing around with recording and maybe pursue music as a career by leveraging what they can do on their own. And so I view these tools as sort of in the same vein, where the idea is not to sort of replace musicians or songwriters, but to enhance them. So basically give them something that they can play with. The other thing that I find interesting that could be quite useful for this is, if your first language isn't English, but you want to write a song in English because you're living in an English-living country, this tool might be helpful because it does provide well-structured sentences. It might help you write your song because you can provide the context and sort of the themes, and the model would help you write in a way that's more natural sounding English than what you would be able to come up with on your own.
Okay. And you mentioned that one of the things the artist is able to do is put in kind of the rhyming scheme that you're interested in. Is this kind of a filter after the model is generating possibilities, or is it some kind of constraint that's introduced in the model itself?
It's not even no constraint or filter. The way it's happening is by nature of how we're training the model. So I have, as I mentioned, we moved to this system where we have two models. Okay. So one is what I call the structure model. So they're both transformer models, but the first one is trained on the lyrics data set, but rather than using the English words, I convert them to their parts of speech. So like noun, adverb, that type of thing. And it also includes like the number of syllables in the line and then the final phoneme syllable. So like basically this is for rhyming. Mm-hmm. And so this model, if you give it the structure of your current line, the output of it, what it generates will be the structure of the next line. And so then you can feed that next line structure with the actual English words of your first line into the second model. And this is another transformer model, which I call the vocabulary transformer. And so this one is trained on books, on the books data set, because we want the diverse vocabulary from that. Mm-hmm. And so what this model is trained to do is to fill in these blanks, so these parts of speech. So the first half gives it the context, right? Because it's using English words. The second half gives it the structure, so the number of syllables, what parts of speech, and the last phoneme. So we trained it with the books data set by essentially, because we know the ground truth, we can specify when you have this context and this structure, this is the last phoneme, and so the target that we're training to emulate matches that. So it rhymes really well. The one thing that we're working on right now is that the easiest way to rhyme is to just use the same word. Right, so red always rhymes with red.
Right.
So that's something that we're exploring a few different approaches on how to overcome that. Mm-hmm. So that we've tried a few things, playing like the first things we tried, just again playing with the data to see if we could discourage it from rhyming with the same word. So far, none of those things have worked very well. So, like an easy thing you can do is basically when you have the the weights for the possible tokens that the model can emit, just set the weight to 0 for the word that you don't want to rhyme, and then the model is forced to pick a different word when decoding. So we're trying a few other things that are a bit more exciting for us. But yeah, that's essentially how we get the rhyming for the model.
Is this project, has this been published? I know you're working on the website, but like...
We had a paper in the workshop, the creativity workshop, 2 years ago.
Okay.
It was last year, sorry, in the creativity workshop at NeurIPS in Montreal last year. But it's a 2-page paper. I think it's on archive, but it's very summarized. It's too. Remember, somebody asked me that wanted to collaborate on the project. I sent them the link, and he's like, "This looks like a proposal. It's not a paper." So yeah, that paper is still very preliminary. We have a more extended version, but we are thinking of submitting it somewhere. We're just trying to refine the model. So the paper itself is not published. But we're working on basically getting more human feedback, because we have some quantitative measures, but because the purpose is creative, it's kind of hard to measure quantitatively. So we want to get more humans to evaluate and measure it compared to other models or even true lyrics. So we're working on that, and also we're working on making the code open source, so you can take it and train with whatever data set you want. So train it with Wikipedia or something, and then you get...
What's the training time or kind of resource for the training?
Well, so we train, we've been training on TPUs, and that's really fast. So the longest...
distributed, like lots of TPUs?
No, just
Okay.
And it's pretty fast. On the order of, like, we were training in less than an hour.
Oh, wow.
So yeah, it's quite fast. The longest part is the pre-processing of the data set. If your data set is very large, because we do this decomposition into parts of speech and that type of thing, that's typically what takes the longest. But once you do it once, and then you can reuse it for whenever.
Interesting. I kind of asked a question earlier about applying external constraints into the modeling process. Does that work with transformer models? Are there folks that are doing that kind of thing, like almost like a model-based kind of...
There is some work with that. I've seen, there's some people in the Toronto office from Brain that have been doing there's one paper called the insertion transformer. So rather than decoding left to right, as you typically do with language models, like, I don't know all the details, but essentially the way it works is now you can emit tokens that say where to insert. So not decoding from left and right, but actually inserting into different parts. So this allows it to potentially start from like a higher level of the structure of the phrase that it's going to generate, and then sort of start filling in more of the details once the structure is there. And so it's actually something I've been meaning to look at, because this might be kind of useful for lyrics where you're trying to satisfy some structure. So maybe we can generate a full verse rather than line by line, if we start doing in this kind of incremental way. There's also, like, from the Magenta team, the music transformer that they've been doing, and that I don't think they explicitly encode constraints, but for instance, the way they encode time is a bit different than what we use for language modeling. And so that just the result of that is for music at least is more coherent and more pleasing. We have started looking a little bit in reinforcement learning and seeing how we could potentially use that.
I was just going to ask, is there an overlap or interplay with our...
There is. So we are looking into it a little bit. It's tricky. It's tricky to get right. And my thinking is always, I don't want to over-complexify it if I don't have to. So that's why I always start with the simplest idea. And if that isn't working, then okay, we start considering a bit more sophisticated things. For many reasons. I mean, when something breaks, it's easier to fix if it's simpler than if you have a lot of moving parts. And I also feel like with the reinforcement learning aspect of it, the little I've been playing with it for this particular project, it's a little harder to make it stable in the sense that you can kind of reproduce the same type of quality that from run to run.
So it might be interesting and instructive to kind of explore, like, what's your first step? How do you think about, okay, you've got this one tool that you know well, RL, you've got this use case area that you want to apply it to. Like, how do you start to even formulate the problem?
This is the way I work. It's more trying to solve very specific problems that I have with. So this is what I'm saying, where I like to start with just a simple thing, because it probably won't work the way you want it. And there will be very concrete aspects that or problems that you have with it at the moment. And so then I like to focus on those particular problems and see what techniques I can use. So for instance, for this rhyming constraint, there is some prior work that has done similar type things, not with transformers, but with RNN. So Natasha Jacques, when she did an internship with the Magenta team, she had a paper where she was using RL for like an RNN that produces melodies. She was trying to use RL to encourage it to respect the rules of counterpoint. So counterpoint is this set of rules from music theory that basically specifies how to write music for polyphonic voices so that it sounds better. And so she was trying to use RL for this because the RNN for melody generation on its own wasn't respecting this necessarily at all. And sometimes it was producing like just repeating the same note over and over, which is a violation of one of the rules of counterpoint. So that she got some interesting results, but I think part of the limitation was also just the RNN. Encoding it into the training process of the transformer, so how you train these attention models, I think that might be a little challenging, and it would likely slow down our training because the technical aspects of it, of getting these RL things working on, for instance, TPUs, is not trivial. Just because TPUs work well on very large batches, but not as well with smaller batches. And with RL, when you're dealing with this kind of online,
at a time.
Yeah. Online. So then it becomes tricky to make it work well in a way that because you still want to be able to train these things quickly.
Yeah. So it sounds like it's much less of a, hey, I've got, chocolate peanut butter, let's get them together and see what happens.
Oh, yeah. No.
Got this specific thing, start at the simplest possible way to solve it. Yeah. And kind of work your way up in complexity.
Exactly. So I don't want to throw RL at, just because I know it well, I don't necessarily want to use it for everything, because sometimes you don't need RL. Like sometimes just, I don't know, an SVM would work just fine. Sure. And then you should just use that in my viewpoint.
And now you've got a couple of papers, a poster and a paper maybe here at NeurIPS, though, that are using RL.
Yes. Yeah. So we had a poster this morning from our team. So Mark Belmar was the first author, and he was the one manning the poster. And I saw him afterwards. His voice was very tired. So that one is called Geometric Perspective on Optimal Representations in Reinforcement Learning. And so we've been thinking a lot on our team in Montreal about representations for reinforcement learning. And myself in particular, I'm quite interested in this topic, and I'm doing a lot of work right now in this space. But this paper is sort of a partner paper to this other work that came out in ICML. I wasn't on this other paper, but I was along for the voyage. The value function polytope. So this is a paper that basically shows that the value functions that you get in Markov decision processes form this polytope in this high dimensional space. And so it has these interesting characteristics. So for instance, the vertices of this polytope correspond to deterministic policies. And so the path, you can look at the path that certain different algorithms will take along this polytope as they try to get to the optimal policy. And there's some really interesting visualizations. So when you compare like value-based methods versus policy gradient methods, and some of them actually leave the polytope in their trajectory. So they're essentially, their policies are in a space where they're not valid policies, in the sense that they're not consistent with the system, but they eventually end up coming back and reaching some near optimal policy. So the work we have here is basically leveraging this polytope and trying to see how we can use it for optimal representations. And what I mean by optimal representations is that it's not just useful for the optimal policy, but you can actually use this representation theoretically for many different policies. So there's a whole theory behind it, but essentially you're trying to find a representation that will minimize the error that you get when you use that representation to express a particular value function for a policy that doesn't need to be optimal. So it ends up being akin to having auxiliary tasks, in a sense, where there's a lot of work in the reinforcement learning field where adding auxiliary tasks to your learning process is helpful, in that it serves almost like a regularizer for your representations.
The multitask.
Yeah, exactly. Mm-hmm. And so these different policies that you're optimizing for, so you're not just trying to get to this optimal policy, but sort of build your representation in a way that you can express these other policies quite well. They end up serving sort of as auxiliary tasks, and they can help make the representation a bit more interpretable, but also more expressive. So there's some visualizations in grid worlds where you can see, if you do the regular learning process, if you look at the representations, you get certain dimensions of the representation are almost useless in the sense that they're not very expressive in terms of the state space of what they can represent in the state space. But using these, we call them adversarial value functions. So these are the value functions for the other policies. As these auxiliary tasks, you get representations that are much more expressive in that they cover the state space a lot more. And so they're able to have a richer expressive power for representing multiple value functions.
You mentioned expressiveness. Are you trying to have minimal representations in a sense that they're reduced dimensionality?
No, not necessarily with this. But so part of what we're trying to achieve is that whatever representation you end up learning isn't overfit to the optimal policy. So let's say you tweak your reward function a little bit, and the policy you have is no longer optimal under this new reward scheme. But let's say for whatever reason you maintain your representation fixed because you just want to do linear approximation. If you don't have a good representation, then you're not going to be able to express the new policy properly. And so this is what these representations are trying to do. Not necessarily reduce dimensionality, but just increased expressive power, so that they're able to pretty well express your current optimal value function. But if you were to want to express the value function under a different policy, or under a different reward function, perhaps, that it would still have the pretty good expressive power to be able to do that with low approximation error.
Now, the concept of generalizability is applicable to both the policy itself and the representation. Mm-hmm. And so is there a relationship between the two, whereas more generalizable or better generalized policies have better generalized representations, or not necessarily unless you apply this approach that you've described?
So by generalizable policies, do you mean like policies that are like if you've learned a suite of policies? Or?
I guess I'm trying to... I don't know if policy is the right place to apply. This is the question I'm asking. Like if I'm thinking of it from the perspective of I've trained an agent that can maximize some reward in some environment. And one sense generalization is I want to be able to put it in a slightly different environment and have it be able to perform well. Right. And so that being the case, where does generalization live in that world? Is it in the policy that or is
you probably end up learning a new policy. Yeah. But this ties very closely to representation, because if your representation, it's almost like you're doing fine tuning at that point. So you've trained your agent under a particular reward function, and now you have your trained agent, and now you say, okay, well, now I want this new task or this new reward function, but I don't want to retrain from scratch. I want to start from where I started. So it's kind of like fine tuning. And so there, if your representation is highly overfit to the first policy that you ended up learning, it might be very difficult to sort of switch over to this new policy. If you're doing something even more drastic, where you're saying, I already trained this agent, so I'm going to fix the representation and no longer backprop through the rest of the network, and I'm only going to be learning the last linear layer. If your representation is poor, you're not going to be able to learn the new task. And so there is where generalization comes into play. If you have a representation that is expressive, then when you switch the reward function or try to learn a new policy, if your representation is expressive, you should be able to do that reasonably well, at least better than with a lot of the existing methods, where there is evidence that they do tend to overfit to the current policy.
Okay. And so what was the inspiration for this paper, coming from the original Polytope paper? Was it driven by a particular use case, or...
So Mark, he's introduced the distributional approach to reinforcement learning. So rather than backing up values, you're backing up distributions when you're doing learning. And so this seems to give a lot of advantages for learning in terms of performance. And there's a lot of follow-up work. I've seen a bunch of papers. Today, particularly, there were a lot of distributional papers. but it's still not well understood why they're giving that advantage. So we had a paper, Triple AI this year, with Claire Lyle, where we were investigating where this difference comes from. So the traditional way of doing the RL backup is, we call it expectational, because you're taking expectations and then you get a single number, versus the distributional approach where you're backing up distributions. And so Claire did a lot of work, and she essentially proved that there is no difference under certain mild conditions. There is no difference between expectational and distribution, neither in the tabular setting nor the linear function approximator setting. So they're essentially identical. Distributional doesn't give you an advantage then. It's really when you go into deep networks that the advantage of distributional comes in. And it's not always guaranteed to give you an advantage. So it's just going to be different. And so sometimes it might actually hurt you. There's a counterexample in the paper where it shows that distributional can actually provide worse performance than expectational. So we, in our team, we're also very interested in trying to understand distributional methods more. And so Mark was looking into this quite a bit, and he came up with this idea of basically looking at at the distributional perspective, almost like as auxiliary tasks. And through that, he had I remember a good lunch meeting with Dale Schuurmans, and I think that's where they came up with this idea of the adversarial value functions. But it came from this initial idea of, let's try to understand distributional methods a bit.
Okay. And you've got another paper that is being presented in the financial applications workshop.
Yeah, so this is a collaboration with the Bank of Canada. I mean, they've done most of the work. I'm more on an advisory, on an advisory role. So a lot of them, their team, they're economists, so they're not as familiar with reinforcement learning. So that's where I come in, and so I just basically, they show me what they're thinking, and we had a lot of brainstorms at the beginning to try to frame the problem properly so that it sort of satisfies their desiderata for their economic theory, but also that it makes sense from a reinforcement learning perspective. And so what they're looking at, they're part of the Bank of Canada, which is part of the government. And one of the main tasks of the Bank of Canada is to make sure that the economy is stable. And so one of the things they look at is the interbank payments that happen on a daily basis between different banks in Canada. So Bank A owes Bank B some money, and so it may send it throughout the day. And so if Bank B has that extra liquidity, then Bank B can pay other banks. And so how they manage these payments affects how many of the payments they can make and how many payments they receive. And so not making payments in time can give them interest penalties and these types of things. And so the Bank of Canada plays a role as an intermediary to try to regulate these things so that you don't have problems where there's a bank that's not making any of the payments and all of the other banks are stuck and not able to make any other payments, and so you're stuck in this stalemate. So it's a very complex problem. It's a very dynamic problem, and they're interested in looking at this obviously from the economics theory perspective, but also they're interested in seeing if you can simulate some of these dynamics via reinforcement learning. So we've been looking at framing it as a multi-agent reinforcement learning problem, where each of the agents are the different banks in question, and trying to train them to learn optimal policies, and they're co-learning. So all of the agents are sort of learning independently, and you get some interesting dynamics as this is happening. So the paper that we have here is still very preliminary work, where we're essentially trying to demonstrate that this is even feasible. So as I said, I like to take things from the simple angle and then grow from there. So we're decomposing the big problem of solving this interbank payment system, with decomposing it into smaller subproblems that we can analytically find a solution for. That's what the economists know how to do well. And we can sort of validate that reinforcement learning is able to simulate that faithfully. And so far we've had pretty good success with that. And so now we're starting to combine some of these subproblems and go into the more challenging tasks.
What are some examples of the kind of granularity of the subproblems?
So the two subproblems we're considering in this paper, the basically the simplest that you can consider. One is each bank at the start of the day can choose how much liquidity it's going to bring in to start making payments. So it's a prediction problem because you have to, this one is almost like a bandit problem because you choose initial liquidity. It's like basically pulling one of the bandit arms. And then based on that initial liquidity, that determines how much you'll be able to pay. So obviously, if there were no cost to that, you would just pull all of your liquidity, and then you'd have as much money as you need to make all the payments. But there's a cost to pulling initial liquidity, because this is coming from the Bank of Canada. So it's almost like you're borrowing money from the Bank of Canada to be able to make payments, and then at the end of the day, you return it to the bank. So this is one of the sub-problems. This one's more like a bandit problem. So they've run some simulations with log data, historical log data that they have. And then the other problem is the intraday payment. So if you think of the day divided into hours, at each hour you can make a decision of paying a particular bank that you owe money to, or not. So you may owe money to a bunch of different banks. If you don't pay them back, then that bank might not have enough liquidity to pay you back. And so when you start adding more agents, then this becomes more and more complex. And so this one is less of a bandit problem. It's more of a sequential decision-making problem. And in order to decompose them, for the first bandit problem, we're essentially keeping the intraday payment fixed, in the sense that the choice that you made at the beginning doesn't really affect the dynamics of what happens later. It's a fixed policy. And for the second problem, we're essentially assuming giving the agents as much liquidity as they want. Okay. So the problem is very simple there. All they have to do is make all the payments that they need to make. But because there's this multi-agent interaction, they don't necessarily always will find that optimal policy.
When you first started describing the problem, one of the thoughts that came to mind was kind of a graph of the individual banks. I don't know that I've heard much conversation about kind of the intersection of graph and reinforcement learning. Is there work happening there?
There's a little bit, especially in the deterministics. I believe I saw a paper come out recently where they're basically using graph algorithms for solving certain reinforcement learning tasks. So you can do value function approximation by using different types of graph learning algorithms. In this particular case, I mean, they are basically representing a graph, the connections between these
kind of the actual transactions, though, not necessarily structural thing between the banks.
Right. And so most of the work I've seen at the intersection of graph, whether it be with neural networks or not, and reinforcement learning is in the single agent setting, where the graph is more representing the environment. Right. Whereas in this case, the graph is representing the connection between the agents. Right. So you have multiple agents that they're not sharing parameters, so they're kind of independent agents. Right. And the multi-agent setting, it's not something I have done a lot of work on, so it's also been kind of interesting for me to learn more about the literature. It's a really challenging problem. You have a lot of game theoretic aspects to it, and it's not a clear. For many problems, there's no clear solution. You have like Nash equilibria, but that's as good as you can get for many problems. And so I haven't in that space. I haven't seen much with graphs. With graph theory.
Cool. Well, Pablo, thanks for taking the time to chat with us and share a bit about what you're up to.
Thanks so much for chatting with me.
Yeah, absolutely. Thank you. All right, everyone, that's our show for today. For more information on today's guest, visit TWIMLAI.com/shows. Thanks so much for listening, and catch you next time.